Hello PCH people, this is our last video of the year where we will be looking at the definite and indefinite integrals. We looked earlier at limits and then we looked at derivatives, which are the limit of the average rate of change, basically the slope of a tangent line. We will now be looking at an accumulation under a curve, which will also be a limit as the number of rectangles goes to infinity. So they're both connected by limits. So let's start in this. We're going to start off with, if you were able to run at a constant rate of change, the graph would look something like this, where the y-axis is your velocity, feet per second, and the x-axis represents seconds. To figure out how far you ran, we could just use distance equals rate times time. So your distance equals rate times time. Here you had, like I said, the y-axis is your velocity, the x-axis is the time in seconds. So the area of each little box represents, since area is base times height, and I'm going to write it as height times base. The height is feet per second. The length of your base is seconds, and so when you multiply those together, you get feet. What that means is we can find the distance you travel from t equals 1 to t equals 9 as just looking at the area under the curve. So if I sort of highlight all this, that area, we could count boxes, but because it is a constant rate of change, it's a little bit easier. So notation-wise, what we're finding, oops, still have my, we write this little s, which means a summation of all your area from t equals 1 to t equals 9. Our rate is 6 feet per second, and then the length of the base is represented by dt. So to find that area, the height of this whole rectangle is 6, the length of the base is 9 minus 1, this distance here. So that gives us 6 times 8, which is 48 feet. Because we had feet per second times seconds, which is your dt, there's the distance traveled. Now we don't need calculus for that because that's just straight up geometry, finding the area of a rectangle. Calculus comes in when the rate that something is traveling is not constant. So then we have to use other techniques to find that accumulation of whatever it is we're looking for under the curve. There are several methods that you will start doing when you take calculus. Before you get into the actual calculus of it, you will be approximating. And you'll be approximating by finding, like we did, the area of each box or each rectangle. So we could make rectangles underneath this curve. If we make a rectangle, for instance, up here we're going to be again making rectangles from starting at 1 and ending at 9, but we're going to make several rectangles. If I make a rectangle, do I use the right hand side as the height, the left hand side, or the midpoint? Or even better yet, I could use trapezoids. You are going to be using all those methods next year, but we're just doing a little overview, so we will be using the midpoint of each interval. And then we'll add up the area of each rectangle, and that will be an approximation of the accumulation. That approximation is called a Riemann sum. All right, so let's look at how we would do this. We are going to show how to approximate the area using the midpoint rule and 4 rectangles from x equals 1 to 9. So we start off with our diagram. Let's make our 4 rectangles. So I'm going to use my, well, first of all, that means my delta x is 9 minus 1 over over the number of rectangles, that's your n, which is 4. That tells me that, so 8 divided by 4 is 2. 2 is going to be the length of each rectangle. So each one of these is going to represent our delta x. And for purposes later on, these two symbols, delta x equals d of x, dx, are the same thing. All right, so the midpoint of that first interval is going to be at 2, so I draw a horizontal line through that and complete my rectangle. The next interval is also a length of 2, so I make a horizontal at the midpoint and draw my sides. Then the next interval, also a length of 2, so at 6, I draw a horizontal and drop my sides, and then at 8. So we draw a horizontal through there and drop the sides, and that represents the 4 rectangles that we're going to use to approximate the area under this curve from 1 to 9. So how do we write this? From 1 to 9, in this case it's f of x dx. F of x represents the height of the rectangle, and dx represents the delta x, the change, the base, basically. So what we have up here, right here, this is going to be, that point is f of 2. This point represents f of 4, that's your height. We have f of 6, and we have f of 8. So if we had a function that we knew described this, we could actually plug that in, but in this case what we're going to do is approximate. So how does that look? Well, I have a common distance of 2 for my base, so I'm going to actually factor that out, make this a little bit shorter. On the worked out notes, I wrote it out and then factored this out. That 2 is then going to get multiplied by f of 2, f of 4, f of 6, and f of 8. So each one of those represents base times height, base times height, base times height. You're finding the area of each rectangle, where the f of 2, f of 4 is the height, the 2 is the length of the base. And so looking at our graph, I can approximate. So the f of 2 looks like it's at 5. F of 4 looks like it is at 6. Oops, I'm adding this. And then f of 6 looks like it's, we're going to just approximate this. You'll be doing a lot of approximating in the beginning. And f of 8, I'm going to put down as 7.2. And when we then add that all together and multiply by 2, the answer is approximately 50. Now I don't know what the units are. Let's say this was feet per second again, and this is seconds. That would be an accumulation of 50 feet. That would be the area under that curve. So that is one way. You'll be doing things like counting boxes. You'll be using the right-hand rule, where you use the right side of your rectangle to determine the height, the left-hand side. Then you'll also be doing trapezoids, which is an even better approximation. So all of these different approximations are things you can use calculator programs for. So numerically, what are we doing here? We just did that graphically. We can use our Riemann program, the one that I gave you, and if you don't have it, it's okay. There is no expectation that you have to use a program here. But I did, when I gave you guys the quad program, I also gave you something called the Riemann program. And so if you want to tune in for the live Zoom next Monday, I will be showing you how to use that program to find exact approximations. So that equation up there was represented by this f of x, and then you could enter that function into y1, and actually you can set your delta x equal to different features. Now the idea is that was a rough approximation, because look at, there's bits that are sticking out and bits that haven't been counted, bits that we overextended and bits that we underextended, with the idea that, you know, the overextension and the underextension kind of cancel each other out. And you can see if we did trapezoids, how that would be an even better, because a trapezoid would kind of follow the curve a little bit better. But the idea being, the more rectangles that we can make, the smaller the width of the base, which means it will follow the curve a little bit better. And so that leads us to the idea or the definition of a definite integral, where the limit as n approaches infinity, n is the number of rectangles. As you let the number of rectangles go to infinity, and you then sum up all those rectangles, it gives you the exact accumulation under the curve, which is we write like this. So Leibniz was the one who gave us that little s, that little symbol, and that means from your lower bound to your upper bound. F of x is like the height again, d of x is like the length of the base, and that finds the area under the curve. I don't like to say area, it's really an accumulation because it doesn't always represent area. Sometimes you'll get a negative integral, and that's okay. So again, verbally, if we let the number of rectangles approach infinity, then the Riemann sum from a to b on the x-axis will equal the definite integral. So if you want to kind of play with, I have a link here. I'm not sure, I've never tried this in a video. Let's see what happens if I hit that. Will it go there? No, it won't. But you guys are able to click on this link and play with the different values, and you can see, you can just have a slider and look at when you have the number of rectangles get bigger and bigger and bigger, which means each rectangle's width gets smaller and smaller. You're basically fitting everything right under the curve. You can also do that with our Riemann program. And again, it's not required, but it is really helpful to see it as a visual. So I'm going to mark up this diagram for those of you just to see the idea. If I start making all these rectangles, I increase the number of rectangles up here, notice that I'm doing it very quickly, but each rectangle is going to, if it has a very small width, is going to follow the curve a lot better, so there won't be as much over and under approximation. And the idea being that if you actually let that limit go to infinity, what you are doing is filling in all this area and getting an exact approximation. Okay, that's your intro. Well, just like with derivatives, where we did them the long way, finding the limit of the average rate of change using the H form or the C form for the limit, and then we found that there was a shortcut, a nice kind of formula for finding the derivative of a polynomial, which I will remind you of right here. So when we were finding the derivatives, we knew that if f of x, again, it had to be a nice smooth curve. If it equaled a times x to the n, because we only looked at polynomials, then we knew that f prime of x equaled a times, you could bring down the exponent, and then you reduce your exponent by 1. So n times x minus 1, and it gets multiplied by whatever the coefficient was. Well, we also have that for what we call antiderivatives, which means that if I give you the derivative of the function, what was the original function? So that would be called an antiderivative, or an indefinite, because we're not finding it between any two specific lower bound, upper bound, just what's the formula. So this is a little bit harder to, usually I have you guys do this as sort of an exploratory, what can you come up with? So what your thinking should be is, if the derivative is 1 power lower, then if I have the derivative, I know the original function should have been 1 power higher. So if I started with x squared, I knew my original had to be x cubed. Now, I also know that I had to have brought down that power of 3, and I ended up with 12 for my derivative. So what was the original function that got multiplied? Because taking this derivative, I bring down that 3. So 3 times what would give me 12? This would be 4. So your original function is actually 4x cubed plus c. Now the idea behind this is if I had f of x, we're giving the whole family of functions, because what if this was a cubic and then it had plus 5? When I take the derivative of a constant is 0. So I don't know if there was something there or not. So when we have an indefinite and you're taking the antiderivative, you're always going to add plus c. That's actually a point on the AP test. In terms of every free response question, you always add plus c. All right? Okay, well, let's kind of see on this next one. So we know that x squared should be x cubed. We knew we had to bring down a 3, but we ended up with 9. So that means there was an original 3 there, because if I took that derivative, I'd end up with 9x squared. On the next one, I know x had to start being by x squared, and I would have had to bring down that 2, and there is a 2 there, so I'm just going to leave that as is. And then the 3, well, that's like 3 times x to the 0, so 1 power higher would be x to the 1, which means I had to bring down a 1, but there's a 3 there, so I have to leave a 3 there. So this answer will be 3x cubed minus x squared minus 3x plus c. All right, let's try another one. So 5x to the 4th, that means this had to originally have been a 5, but bringing down that 5, if I took the derivative, that 5 is there, so there shouldn't be anything there before. Then we have the x cubed. We know before that would have to be 1 power higher, because the 4 would come down, but there's a 6 there, so that means if a 4 came down and I want to end up with a 6, you know, 3, what would I multiply 4 by to get 6? Turns out, and I'm giving you the reduced form, you'll see where that comes from in a minute, minus 4x, so this had to have been an x squared. And then we know if we took that derivative, a 2 would come down, but I have a 4 there, so there has to be a 2 there to have given me this result of 4. And for the 10, we know that there'd have to be an x to the 1. So this answer is x to the 5th plus 3 halves x to the 4th minus 2x squared plus 10x plus c. So the idea is if you are given a function and you have to find the antiderivative, it will be 1 degree from whatever that derivative was. And what you will find that we have done, we're going to generalize this in a second, the coefficient is going to be divided, or the whole term really, by n plus 1. So can we come up with a formula? Yes, we can. I'm not sure where that's from. Yes, we can. Oh, is that Blue's Clues or something? I forget. It's been a long time. Anyway, so here we have, if f of x is x to the n, I guess I could put a coefficient in front of that, but it doesn't really matter. Then the antiderivative, which we give a capital F, is going to be 1 degree higher, and then you divide your function by whatever that n plus 1 is, plus c, if it's indefinite. So f of x is the antiderivative, which is equivalent to saying the indefinite. Well, the indefinite integral involves another, but it's related to the indefinite integral. Indefinite, what am I writing here? Integral. Can't talk and write at the same time. Of f of x. Of f of x. Now, let's verify that, okay? So we have f of x is x to the n plus 1 times n plus 1. So let's find f prime of x, our generic formula. So how do you take the derivative? So we would bring down the n plus 1, right? And that's going to get multiplied by whatever that denominator was, because that's just a number. And then x to the n plus 1 gets reduced by 1. And the derivative of a constant is going to be 0. So when we simplify this, this cancels the 1 and the 1. And notice you get back x to the n. So that is our formula. Instead of taking down a power, you're raising it a power when you go backwards. So we're going to get ourselves a little bit of practice with this. Down here, number 1, I have f of x equals 12x squared minus 8x plus 5. So let's do these, show the work, and then we will simplify it. So what do I have? I'm going to have big F of x, the antiderivative, is going to equal 12 times x to the n plus 1 will be 3 divided by 3 minus 8. This will become x squared divided by 2. So everything's going up 1 plus 5. X to the 0 becomes x to the 1 divided by 1. And then plus c. So if we simplify that, we get f of x equals, so 4x cubed minus 4x squared plus 5x plus c. And again, obviously you can take an antiderivative term by term just like we could with derivatives. All right, let's try another one. Here we have the f of x, so this is going to be x to the 4th divided by 4, which means this will become a 5. Then we get x cubed divided by 3, so that'll become a 2. Then we have x is going to become 1 plus 1 is squared divided by 2, so the 2 is going to go away, plus 10x plus c. So you can kind of just go straight there, a little bit easier. Now if you're given a radical, or I wish I had given you, you know what, I'm going to add an example here, even though it's not on your notes. I'm going to add 1 over x squared. All right, just to see how this works. So I can't do 1 over x, and we'll talk about that later, or you'll see as we do this one. What I recommend, if it comes to you as a radical, let's write these all with fractional powers or negative powers. So this will be 4 times x to the 1/2 minus x to the 1/3 plus x to the negative 2. That makes it a little bit easier to find your antiderivative. So we're going to have x to the 1/2. Now, to get into the pattern, when you're adding 1, it's really adding the denominator and the numerator together. So this will become x to the 3/2, so that's adding 1 to 1/2. And instead of dividing by 3/2, just get used to multiplying by the reciprocal, which, right, dividing by a fraction is multiplying by the reciprocal. So 4 times 2/3 is going to give me 8/3. So I'm multiplying that 4 by the reciprocal. Then I'm going to have minus x to the 4/3. Just add your numerator and denominator to get the new numerator. You're adding 1 to it. And then I'm going to multiply by the reciprocal, which is 3/4. And then x to the negative 2, if I add 1 to that, that's x to the negative 1. Notice that's why I can't do 1 over x, because you would get x to the negative 1. You add 1, you'd get x to the 0. It just doesn't work, because you can't then divide by 0. You can't divide by n plus 1. It has its own little rule that I'll go into later. So far we did x to the negative 2. So x to the negative 1 divided by a negative 1, which changes this to a negative. and then plus c. So that plus became a negative because you have a -1. And that would be your antiderivative. All right, so each time you're basically just doing this rule up here. And then this is just a number that gets divided or multiplied, depending on whether it's a fraction or a whole number, by whatever coefficient already lives there. And then don't forget your plus c if it's an antiderivative, because we don't know what the full family was. Now, if you're doing a definite integral means it's defined within a particular boundary, so we're actually going to get a numerical answer like we did on the first page. So let's look at how this differs. So antiderivative, notice there's no numbers, no lower bound, no upper bound on my integral sign. So I'm just going to go ahead and do my antiderivative. So 6x squared is going to become x cubed divided by 3, which makes that a 2, minus 2x, that's going to become x squared divided by 2, which will cancel the 2 that's there, plus x plus c. That would be your answer. Do not forget that plus c when you have no limits. However, if I do have limits, like I do here, same problem, here's how that works. Think about back to when we did the constant running. The 1 to 4 is kind of like the length of your base. So I'm going to have my antiderivative, which we've already found. So that's 2x cubed minus x squared plus x. And we are evaluating that from 1 to 4. So what we're really doing here is we are taking, this is really your part of your fundamental theorem of calculus. The answer to this, a definite integral, is you take the antiderivative, evaluate it at that upper bound, minus the antiderivative evaluated at the lower bound. So first I'm going to plug in 4, and so that's going to give me, I hope I have enough room here, so 2 times 4 cubed minus 4 squared plus 4. And then we're going to subtract, plugging in 1. Subtract 2 minus 1 plus 1. So basically, those are going to go away. So we're going to subtract 2, and the final answer is 114. So the answer to a definite integral is an actual accumulation of the area under that curve from 1 to 4. And actually, your calculator can do this as well, but you're not going to be touching a calculator probably a good part of the first quarter, definitely, if not semester, of calculus, because you want to know how to do these by hand. After all, the calculus is calc, no calc. All right, now we have sine. Now we did talk about the derivative of sine. The derivative, which is, we would write it like this, of sine x was cosine x. We looked at that in terms of the slope of any tangent line corresponded on a sine graph, corresponded to your cosine graph. But now what we're going to do is an antiderivative. So here is your sine graph, keeps going, and this would be at 0, this would be at pi, we know this is at 1. What we want to do is find the area under the curve, but we want to first know what is the antiderivative. So what you're going to find is you're going to get a lot of formulas. You're going to get formulas for all your trig functions, combinations of your trig functions. So there is going to be a lot of memorizing of what these are. Some of them you can derive. I'm just going to kind of give you this one. The antiderivative of sine is minus cosine x plus c. So now that we know that, let's see if we can find the area under this curve from 0 to pi. So that means I take the antiderivative of cosine and I evaluate it from 0 to pi. And you always plug in the upper bound first. So we're going to have minus cosine of pi is a -1, and then minus the lower bound is going to be minus the cosine of 0. Cosine of 0 is 1. So I have here 1 plus 1. The area under this curve is 2, whatever the units are. 2 radians, I guess. Radian squared, it's area. All right, and just so you know how the joke on the calendar works, if you had 1 over x, because you can't take that antiderivative, x to the -1 would mean I'd have x to the 0 over 0. Obviously that can't exist. So the antiderivative is the natural log of x. And again, this is going to be a big derivation that you will do in calculus, but since it's a log, the antiderivative is a log plus c, so a log house plus c, because you were taking the antiderivative of 1 over a house, so it's a log house, log cabin plus c, which also could be seen as a houseboat. It's kind of a joke. There you go.